Welcome back, everyone. So today I continue with what I was presenting yesterday, so descriptors. And so yesterday I presented, just as a recap, I presented the descriptors that were based on a first rotation invariance and then symmetrization with respect to permutations. And today I will present descriptors that are based on the kind of the opposite way. So where we start from a permutation invariant descriptor, and then we symmetrize with respect to rotations. Okay, so let's do that. So that will be the first part of today. And in the second part, I will talk about parametrizations. Permutation invariance, then rotation invariance. Okay, and so first, basically what makes things work, I would say, is the so-called, I don't know if many people call it like this, but it's sometimes called like that, the density trick. And so the idea is to consider a density. So this density will be so depends on the atomic positions and is defined as a function which is a sum of atomic density. So we have our nuclei configuration, which is R1 to R capital K, and then we consider a density. So we choose a function, so that's the G here, and then we compute we sum over all these densities shifted around the atoms. So if, for example, I take G as a Gaussian functions, what I will have will be some kind of peaks around the atoms. Okay. Okay. So one advantage of this density is that it's clearly permutation invariant. So if I permute two atoms, then I just have the indices here which are permuted, but since I sum over them, I don't care, basically. And one advantage is that it is often a smooth function in terms of moving the atoms. So it's smooth as a function of atomic coordinates.
You have different types of atoms. I presume you choose a different function.
Yes. Yeah. Otherwise, you exactly, yeah. Otherwise, you lose the. I mean, you use the fact that it has to be invariant only with respect to identical atoms. Yeah.
You can have a different density for each atom type or different G functions with one name.
So I would say it depends on the model you use. So at that point, yeah, I cannot really say. Okay, and I will try to explain why it can be useful to consider such a density. And I will consider a 1D toy example where, so I will go back to the polynomials. And so I will consider a basis of, so I completely forget about the rotation invariant for a moment. And I consider a basis of permutation invariant polynomials. So a typical basis for such polynomials are just the symmetric polynomials. So the first one will be just, so I consider the variables being x1 to xn, and I consider that all particles are identical, and so x1 plus x2 plus xn is a symmetric polynomial. And then if I go to degree 2, then I will have x1, x2 plus x1, x3 plus etc. up to xn minus 1 xn. And then I can go all the way to x1 times x2 times xn. And this is the basis of symmetric polynomials. So basically, you can construct any polynomial with these polynomials, or I mean, and if you only go up to degree n, then you only need those polynomials. Okay. And so then the question is how expensive it is to evaluate those polynomials. And so here, if you count, so here you have basically n terms. Here you have more or less n squared term. And in general, what you have is n choose k terms, which where k is the degree of the polynomial you consider. And so this is bad in the sense that here it's not exactly n factorial, but it's kind of hidden here. So in some way, so for example, if you consider distances here, then you will have to pay the price for the n factorial. But sorry? Yes, exactly. You have 2 power n term in total. Yeah. Okay. And but you can also consider an alternative basis, which is, okay, so it doesn't change for the first polynomial. So it's just x1 plus x2 plus xn. And then I consider x1 squared plus x2 squared plus etc. plus xn squared. And then I go all the way to x1 to the n plus x2 to the n plus xn to the n. And so here, if we have for all polynomials, we only have n terms. And we generate the same space. So for example, if I take so this polynomial, so x1 squared plus x2 squared plus xn squared, this is just in this here, x1 plus xn to the square minus 2 times the x1, x2 plus etc. So basically, those 2 bases are really just 2 bases. They span the same space. But when you evaluate the basis functions, the computational cost is completely different. And especially here, you can just, in terms of computation, you pre-compute x1 to the n, etc., up to xn to xn to the n, and that's basically n squared terms, and then that's it. Then you only can, so if you want polynomials of higher orders, you can just multiply those things, but they always only depends on these polynomials. So it's, in a sense, it's really efficient to do something like that. And so here, somehow to link this to the density example here, it's the same as if we were in 1D and we would take G as just the monomials. So x squared, x cubed, etc. Okay, and so in 3D, basically, we have an additional step to do, which is we have to symmetrize over rotations. Okay, and maybe one last comment. So if you consider the case of the molecule and you consider an atomic environment, so as yesterday we will consider a cutoff radius and consider all the atoms within the cutoff radius, but actually this number of neighbors doesn't cost as much as yesterday. So yesterday, since we were explicitly summing over all the neighbors, if we have lots of neighbors, then this will increase the computational cost, while here, basically, this is way milder, this dependency in the terms of number of neighbors. Yes?
What is the link between the toy example here and the density?
So here it would be the same as considering G of X is X to some K. Then you shift and then you take the power, something like that. And in general, for some descriptors, you just consider, so either you choose some density or you choose a basis that, several densities that correspond. Yeah, I will explain this, but basically you project this density onto some basis and then you look at what happens. Okay. And so, yeah, so that's exactly this. So, when we consider body-ordered functions, what we do is basically consider products of such densities. And so for the two body, we have, so this is just the density as I mentioned. And then a three body would be based on a correlation of two densities. So then, yeah, it will highly depend on the construction of the descriptor, but you can see it as something like rho 1, rho 2 of X, and with some kind of definition, and for body, it would be kind of the same. Rho 1, rho 2, rho 3. So that's one way to see it. The other way is to say that we project this density onto some basis. So we take a basis function phi b, and then we project this density onto this basis. And then if we go to higher body order, then we would consider some kind of tensor product of these basis functions up to some correlation order mu. And then we would similarly consider tensor product of the density to some power. I will give precise examples afterwards. Sorry? Yeah, I mean, yeah. So what I was saying is that then it depends how you construct the descriptors from that. So somehow you consider correlations. So yeah, you have different x's, but then basically then you need some kind of integration because this is a function, and at the end we only want the descriptors will be a vector, so a list of scalars, and so we need somehow to the whole density is too much information somehow, so we need to project it and And this is what is highly dependent on the proposed methods. And so this is what I will present now. Okay, and so so basically to enforce the rotational symmetry, what we will do is we will typically integrate over the H measure of rotation over the rotations. And here the Wigner matrices that I talked about yesterday will appear again. So I will now present the SOAP descriptors. SOAP means so that's smooth overlap of atomic orbitals. Is written SOAP, and this was proposed by Bartok, Kondor, and Chani in 2013. And so here, the idea is to choose a density that is Gaussian. So the density for a configuration is written as the sum of exponential minus alpha x minus Ri to the square. And here I always consider that I only have one chemical species. Otherwise, the things get more complicated. So I will stick to this simple case. So here, basically the G of x that was here just before is just a Gaussian with some parameterized width. Okay, and so then what they say is that they expand this density onto in the basis of spherical harmonics. So somehow here, since we are dealing with rotation, we don't really have a choice but looking at spherical harmonics, because this is the right basis to use. So the second step here is to expand the density with spherical harmonics. And a nice thing here is that this can be done explicitly with when you have a Gaussian function. And so I won't write the explicit expansion, but what happens is that then they use a radial basis and an angular basis. And so then what they do is that they expand this density as a sum over, so n is the index for the radial basis, and then there is a sum from L equals 0 to infinity, then m from minus L to L of C n L m of R, G n of small r, Y L m R hat. And so here, these coefficients can actually be easily computed, because the hidden somewhere are some Bessel functions. And so, I mean, things are known enough that it's possible to compute these. Okay, yes.
When you expand on a spherical basis, it means implicitly that you choose where is the center of
Yes.
the expansion, and in an absurd situation where you have a lot of atoms, so you choose the center of mass.
So somehow you choose. So I would say that here, since then we only predict. So it will be used to predict the atomic energy. So the energies of atomic environment. There is a natural center, which is the place, the center of the reference atom. So basically, if we have a molecule here, then we say that the energy is the sum over K of the local energies, and these energies are centered around an atom. And so here the center to use here is basically this.
Okay, because I might be confused that the R that you wrote there is not.
Yeah. Okay. So yeah, I agree. It's confusing. Yeah, it's not so clear, but in that case, I would say it would be more like looking at R minus RK, kind of
Okay,
than
so
the
full collection of atoms.
Yeah, it's the collection of atom minus one. Yeah, you remove you would center.
Okay.
Yeah, exactly. It would be for
every K.
Then at the end you sum over all K's, and so you have something where you have the center that is natural. N is for the radial basis. No, I mean it depends. If you want the exact, so I would say in practice you truncate. So in practice you would say that you have if you go up to infinity, then this is an equality, but it's only valid. It's only an equality in the limit. Yes. Okay, so this depends on your system. I don't really have a precise answer to give. It really depends on the side of the range of the interaction. Usually you kind of consider it reasonably small. So I would say for materials, you would maybe go to like second nearest neighbors or something like that. Yeah, but I cannot answer precisely. Yes.
Sorry, it's possible to ensure that the function remains smooth with respect to atomic positions if you have a radial cutoff.
So you take a smooth cutoff function.
So that's
basically
zero derivative.
Yes, you impose some kind of regularity on the derivative at the cutoff point.
So here, this form is only designed for Gaussians, or you can put other functions in.
So in the subdescriptor, they said we start from a Gaussian and then we obtain coefficients here that are explicit for this Gaussian. But I will show it for the atomic cluster expansion afterwards. In fact, you can choose these coefficients as you want somehow.
Because all that is to have equivariance when you rotate.
Yeah, we want to have an invariance.
The transformation of the Gaussian in the rotation is very easy. Why not just to equate in the Gaussian instead of using the spherical?
The thing is that since you sum over, you have a sum of many Gaussians, so you cannot just say that I don't know. So I would say it's not that easy to say how it changes when it rotates. And maybe the other thing that will come afterwards is that when you want higher correlation orders, so if you want to go to like a 3-body or 4-body, then this is really a bit more involved.
Mm-hmm.
Yes.
That's one question. If
the small r, the coordinate in the spherical coordinate system of coordinate, the small r.
The small r, yes, it's the, oh yeah, okay. So that this is an x, which would be somehow r hat, where r is the radial coordinate and r hat the angular coordinate. Okay, so then the third step is to project this onto a one body basis. Which is basically computing the scalar product with, so I will assume for simplicity that the radial basis functions are orthonormal. It simplifies a lot the things in the integral. It's possible to consider basis functions that are not normalized, but yeah, it will. So basically what we have here, due to this expansion, is just that if we project onto this basis, then we just get the coefficients. Okay. And then what I want to see is the effect of a rotation onto the coefficients. And so if I rotate, so first the thing is that if we, so I have the formula here. So if I rotate at the same time the nuclei and the x, then the formula doesn't change. So it doesn't change the result. So what we have is that the density rho QR, so for Q in SO3, rho QR QX is just rho R of R. And now if I look at what this is using the coefficients and the explicit expression for the spherical harmonics, then what I have is that, so I still have the sum over NL, and then I have sum over M. So basically I will, this, when I rotate, so I have YLMQR half, then I just have a Vignode matrix that gets out. And so what I have is sum over NL, M, N prime of CNLM to R, because I have rotated the configuration, and then GN of R, and then D, M, M prime, L, Q, Y, L, M prime, R hat. And so here I can somehow group things a little bit differently and have sum over M prime of sum over M, CNLMQR, D, M, M prime of Q, GN R, Y, L, M prime a hat. And so here, by identification, this is just the CNL M prime of R. So I just look at the expansion and I say that here I'm in the basis NL M prime, and so this has to be the coefficient for NLM N prime. And so if I rewrite it a little bit differently, so what I can say is that, so if I consider C and L as a row vector with all the m's, I have that C and L of R is just C and L of QR times the Vignode matrix. And so if I just put the DLQ on the other side, noting that the Vignode matrix is unitary, I get that C and L QR is C and L R DLQ star. So basically, this means that these coefficients are equivariant with and for each L, I get the Vignode matrix of order L. Okay, and so from there, they construct two different types of descriptors. So the first one is called the power spectrum, and is basically an order 2 correlation descriptor. And so a way a way to define it is to say that you take somehow you take the integral of rho and L of QR star, and then you multiply by rho R and L of QR, and you integrate over R and over rotations. And so here, basically, what you get, so you can expand this, and then you get the a product of Vignode matrices, which makes, so a lot of things are orthogonal, so they disappear. So at the end, what we get is just the sum over M of C and LM of R squared. And so here there is some kind of a problem, which is that, oh, sorry, this was an N prime. And so basically, even though you have N prime here, then when you integrate out, you only get the N and N prime have to be the same. So there's a N prime that appears, and so somehow this is, it would be possible to define just some P and L as power spectrum, but it's somehow richer to define the power spectrum a bit differently, and just as the sum over M of C and L M of R star C and L N prime M of R. And so this would be P and N prime R of R. So this is somehow the right definition to take. And so here it's easy to see that the descriptor is rotation invariant. Because basically, if you now compute the effect of the rotation, what you get is just C and L of R. Then you get the product of Vignode matrices. So DL Q star DL Q, CNL of R. And so this is just the identity. And so you get CNLR. There is a star missing here. CNLR prime. There is an N prime missing here. And so here you get just PN N prime L of R. So this descriptor is rotation invariant. And so this is for SO3, and if you want to go to O3, then we need to consider reflection, and it's easy to check that. So the transformation when we just take minus R is minus 1 to the L CNL of R, and so the power spectrum is also reflection invariant. Okay, and so then they define another descriptor, which is called the bispectrum. And so here it's an order 3 correlation descriptor. And so I will just give the formula, and I won't check that it is actually rotation invariant. You will have to believe me for a while. I will come back to it probably afterwards if I have time. And so this is defined as the sum over m's over m1s and m2 and n1 lm star, and then there. So basically, it's a product of 3 coefficients that are then arranged to generate a function that is rotation invariant. And here the object I haven't talked about so far are so this capital C are the Clebsch-Gordon coefficients, and I will explain a little bit more in detail what they are just in a moment. And so this was proposed so in the SOAP paper in 2013, but it's actually also a descriptor that is used in the so-called SNAP descriptor, which is the spectral neighbor analysis potential. It's okay, so it's the same descriptor. It's derived a little bit differently because they consider rotation in a 4-dimensional space, but in the end, what they get out are more or less the same bispectrum as in the SOAP for the SOAP, and this is presented in a paper by Tom Som in 2014, and the descriptor is called hyperspherical bispectrum. Okay. Any question? Yes.
when you develop this one body basis, what is the typical G and like
the G that you use? So in SOAP they use Gaussians.
Okay.
In the G, so the G is the function, you mean?
Yes, yeah, the function G is
To define the density.
yes, right.
Yes. So oh no, you mean the G ends.
Yes.
Okay. This I don't know.
System dependent.
Yeah, I would say so. I would say that. Yeah, I would say yeah, you can use Gaussians or Gaussian times polynomial. I would say you would use something that is kind of similar to what you use in chemistry calculation. So, but then it could be polynomials. But if you would just use standard polynomials, then this would blow up at infinity, which you don't want. So you would use like transformed coordinates, things like this.
Want this to be able to represent not just one density, but like a sum of the density, if I understand correctly, or it is just one density.
No, it's for the sum of the densities. Yes, yeah. So so you would need something like so. So now I think in the SOAP paper they have a plot where they would have something like that, so that then you can, when you have atoms that are further away, you can take this into account. Yeah. And also they say that this is for this reason, since the radial basis function that they use have a small overlap when ends are different, that it's really richer to use the descriptor with a p n n n prime at the same time. Other questions? So I will now move to the atomic cluster expansion. Which was introduced by Drautz. So in 2019, but in fact before that there was a paper by Alexander Chapev where he proposes a method called moment tensor potential, which is the two methods are equivalent in the sense that they span the same space, and then the bases that are used are different, and so in terms of calculations and training and so on, this is a bit different, but in terms of the spaces that are generated, they are the same. Okay, and somehow this will allow for a generalization of the power spectrum and bispectrum at any correlation order. And so here the starting point is take a density as Dirac functions as a Dirac. So rho r of r is the sum of deltas r minus ri. Then exactly as before, we project onto a one-body basis. That here I denoted by phi and Lm. And so in that case, this is just the sum of phi and Lm of Ri. And so here the special dependency already disappears from here. So somehow what we consider is a quantity. So in the following, this when I sum this phi and Lm over the the atoms, I write it as A. So this would be ALM, NLM of R. And so once again, you can typically think of these phi LMs as GNs for the radial part times spherical harmonics. Except that those are the RIs. Okay, and then we consider new order correlations, which are just basically products of such quantities. And so these will be some k equal 1 to mu of A and k and lk and k of R. Okay. And so then, as before, what we want to do is to see how these quantities behave when we rotate, and we want to extract features that are rotation invariant for the moment. Okay, and so so to do so, basically what we need. So this I will so I will write it as A and L M. So kind of take a vectors of the different indices to make this a bit with less indices, let's say. And so then, so basically what we need to see is how the angular part changes when we rotate. Yes.
Here is the right polynomial, right?
Sorry?
So the G there.
Here?
That's I forgot the name. The polynomial using the Schrödinger solution for one atom, or is it still a Gaussian from before?
It can be anything at that point. It's really it's really abstract. So somehow and I mean, in the application you would try to maybe optimize this, but at that point it's kind of we are given a basis, a radial basis, and then we want. I mean, it won't have an impact on the rotation symmetrization.
It needs to be a base.
It just needs to generate the the kind of it's a basis for the space on radial coordinates, basically. Okay, and so okay, so if we look at the just one spherical harmonics, so as before, we have that this is we have the Vignodi matrix that appears. So YLM of QR is just the sum of DL mu Q YL mu of R. And so now if we do that to a product of spherical harmonics, so then, so this I write it with underlines. So then we basically get the same. So here we will have a multi-index mu in some ML that I will define in a moment. And then we have somehow a d mu ML of Q YL M YL mu of R. And so ML here is just the set of mu in Z to the n, where all the indices are between minus L alpha and L alpha. And the let's say multiple Vignadi matrix is just a product of Vignadi matrices. So dl of mu m of q is just a product from alpha equal 1 to n of the d mu alpha m alpha of q L alpha. Okay, so this is mainly to simplify notation, but what happens here is pretty clear. So if we multiply several spherical harmonics, then if we rotate, we get a Vignadi matrix out of each spherical harmonics, and then we get a product of all these Vignadi matrices. For where? No, it's it's a typo. Thank you. And then, yeah, this doesn't matter. Okay, and so then there is the key thing that we will use to see what happens when we rotate everything is what is called the decomposition of so it's called addition of angular momenta. So what happens when you have in fact, you can write the product of two spherical harmonics as single spherical harmonics. And so this is linked to the fact that basically you can decompose the product of two Vignadi matrices as a sum of other Vignadi matrices. So basically we decompose, so the two Vignadi matrices, the Vignadi matrices in general constitute irreducible representations for this rotation group. And so when we multiply those matrices, we don't get irreducible representation, but we have a way to separate this into irreducible representations. And so this is where the so-called Clebsch-Gordon coefficients arise. So that's the addition of angular momenta. And so this is for OQ in SO3. So what we have is that DL1 M1 mu1 of Q, D M2 mu2 L2 of Q is equal to the sum L1 minus L2 to L1 plus L2 of, I'll write it, would be, there is this. And so we get C L1, M1, L2, M2, lambda M1 plus M2, D M1 plus M2, lambda mu1 plus mu2, Q times another Clebsch-Gordon coefficient, L1 mu1 L2 mu2, lambda mu1 plus mu2. So somehow another kind of way to write it, maybe in a more concise way, is that if you look at the kind of the product of DL1 and DL2, you get something like the matrix here of DL1 minus L2 up to DL1 plus L2, and then you have Clebsch-Gordon coefficients here, and so on the left and on the right. So somehow it's kind of a diagonalization of this. I mean, the Clebsch-Gordon coefficients are the eigenvectors of this product of matrices, which allow to obtain a decomposition of irreducible representation. Okay, and once we have that, the other thing that is important, I don't know if I mentioned it before, is that if we integrate over the rotation Wigner matrix, then we get 0 except if L is 0, basically. So this means that in this decomposition, we basically only have, when we integrate, so here, this everything here depends on Q, but the Clebsch-Gordon coefficients don't depend on Q. And so when we integrate out this, then we see that what will be left is only the representations where the index here, the index lambda is 0. Any questions on that?
Can you repeat the explanation for why this is true?
For what way? For
Why everybody is 0 and L is 0? Like with the,
this.
Yeah, you mentioned with using the diagonal.
Oh, no. Okay, so these are two unrelated things.
Okay.
I mean, no, it's more than this implies that this. So, for example, if you take L1 equals 1, L2 equals 1, then you compute D1 times D1. And then what you obtain is that you can write it as a matrix. So Clebsch-Gordon coefficient C times, so then you will have D0, D1, D2. So this is a 1-by-1 matrix. This is a 3-by-3 matrix. This is a 5-by-5 matrix. And then these matrices depend on Q. And then here you have C transpose. And so when you integrate out, because when you integrate out a Wigner matrix, everything is 0 except if L equals 0. When you integrate this over Q, then you only see, I mean, those things will be 0. So basically you get C 1, and then you only get zeros. And so if you want to generate basis functions that are invariant with respect to rotations, then you can only select those who will give rise to the D0 in this representation. That's the main idea. And so this is for when we have two indices, but recursively we can do that at any order. And so what we what we have in that case is that, so here we have the lambda, which goes from L1 minus L2 absolute value to L1 plus L2. And so in general, we have to a set of these kind of lambdas that I will just define as L n minus 1. And so that's all the L's that satisfies the, I mean, the kind of the same as the lambdas that satisfy the conditions. But in spirit, it's just really a recursion over this procedure here. And so we will have similarly generalized Clebsch-Gordon coefficients. And then when we want to generate basis functions that are invariant with respect to rotations, we know which Clebsch-Gordon coefficients to consider. And so if we have M and mu m in the set that I defined just over there, then we can decompose the multi-Vignode matrix, L mu m, as some Clebsch-Gordon coefficients that depend on mu and L and n dl of q, d maybe d tilde, times the Clebsch-Gordon coefficients m and mn transpose. And so this is exactly the same thing. The d tilde matrix is a block diagonal matrix. D tilde is the block diagonal matrix dln of q, so which contains the last index in the decomposition. And so here we have L, which is L2 to Ln in Ln. And just as to make this rigorous, so the MNs are because of the sizes of the different Vignode matrices. And so we have Mn, which is from minus Ln to Ln. Okay, so somehow that's really the same thing, except that now we have an arbitrary number of products of Vignode matrices that we write as some kind of block diagonalization with Clebsch-Gordon coefficients times this block diagonal matrix times the Clebsch-Gordon coefficients. And so now when we integrate over rotations, that's the second part of this result. So we are only left with the terms where the Ln is 0. Okay, and so So at the end, what we really do is that we consider particular linear combinations of these ALMs. So as I defined it before, so that's the product from k equal 1 to nu of A and K L K M K of R. And so the basis functions are BL and L are the new. So the Clebsch-Gordon coefficients L0 times those L M nu. So we basically only keep the terms where which give rise to a last index that is that's 0. Do you want a concrete example when L equals 3? Okay, I can try to give that. So similarly, so if we take L equals 1, 1, and 2. So that corresponds to Y 1, M1, Y2, M2, 1, sorry, Y1 and 2, Y2, and 3. We look at products at all all these basis functions for M1 from and M2 from -1 to 1 and M3 from -2 to 2. And so then to see what kind of decomposition we have at the end, we need to compute this set here, this LL. So when we have only 2, then it's easy. It's just L1 minus L2 to L1 plus L2. So here it's a bit more involved, but we can compute all the L's that are possible. And so in this case, we have basically 5 possible combinations. So 1, 1, 2, 0, 2, 1, 2, 2, and 2, 3. And so so here it's really easy to check that this set corresponds to the L's satisfying this definition. And then the detailed matrix will be the matrix containing the small Vignodi matrices for each of the last indices. So here we will have D1 of Q, D0 of Q, D1 of Q, D2 of Q, and D3 of Q. And the rest is just 0. And so here what this says is that among all those possibilities, we can at most generate one basis function which is rotationally invariant, and this will be given by looking at the Clebsch-Gordon coefficients corresponding to this line and this column, basically. And so these techniques gives kind of an upper bound of the number of functions that we can generate. So with this, we can generate rotation invariant functions. And then the thing is that when we, since we sum, we have this A here. So we sum over all possible atoms. Then it still might happen in practice that those basis functions are not linearly independent. And so there is, at the end, kind of a last step, which is just to a small singular value decomposition of the basis function that are obtained to get rid of all linear dependency. So that's how it can be done in practice. So here, basically, these techniques gives a way to obtain the exact number of rotation invariant basis functions when we don't consider permutation invariance. But then when we put the permutation invariance, and so when we sum over the different like the different configurations, then the different atoms, then we can encounter some troubles. Okay, and this at the end is proven to be complete. So you can basically represent any function that is invariant with respect to rotation and permutation using such kind of method. Which is nice because it says that in the limit where you have like a large number of radial basis functions and spherical harmonics, then you can represent any function. So you can.
So these basis functions that you obtain at the end of the procedure, it's not yet the descriptors, right? Or it is the...
So basically each basis function computed on the configuration is one descriptor. So one element of the vector of descriptors. So so maybe I should add that. So the descriptor at the end is the list of it's the basis evaluated on the configuration. And what happens in practice is that so that's the basically Bn I or something like that, or I in 1 to the number of bases somehow, something like that. So what happens in practice is that we often limit the so two things, so two hyperparameters, which are the correlation order and the degree of the polynomials, the total degree of the polynomials.
Sorry,
yes.
Power spectrum, the spectrum, or two particular? Or...
Yeah, so if you write it like this, then you can just write the both power spectrum, and bispectrum as particular cases of this method. Okay, so that's it basically for the descriptors. And now I will move on to the different parameterizations that are used.
There are some that are considered like the best that everybody uses.
I would say it really depends on who you talk to. So my impression is that most people will say that you have to use their method. So what? So maybe one thing is that people are kind of agree on the fact that if you go to correlation order 4 or something like that, body order 4 to 5, then it's enough somehow. And they don't really know why, but in practice it seems that you don't you don't improve the results too much if you go to higher body order. But also it depends on the parameterization. So as I will show right now. Okay, so now I will discuss the parameterization. So, okay. So, as Gabriel discussed already, the kind of the most simple thing to do is to use a linear method. So, use a linear parameterization. And so the idea here is that the basis functions that are used are just the descriptors. And this is also why in the atomic cluster expansion, I mostly talked about basis functions, because when you do like a linear method, then your basis functions are indeed the descriptors.
And you're talking about the parameterization of the energy.
Yes. Yeah. So yes. And so parameterization, or like a functional form, or for the energy. Okay, so here the descriptors are used as are the basis functions. Okay, so now we look really at atomic environment. And so for an atomic environment, so I will denote it by somehow RKR, where RK is the center atom and R is the configuration around. So that's the full configuration. So that's to denote that we have an atomic environment. And so the descriptors I denoted by, so somehow D R K R P, and P from 1 to the number of descriptors that we have. And so in this linear scheme, the NB, so the number of descriptors, corresponds to the number of basis functions that we have. Okay, and so then what we do is that we write the local energy contributions as linear in the descriptor. So that means that when we have an environment, we write the energy as the sum of over P from 1 to NB of theta P d RK R T. So we have P parameters to fit. And so then the total energy, as before, is given just as the sum of all local energy contributions. So that's the sum from k equals 1 to capital K of the sum from P equal 1 to NB, theta P, d RKR P. Okay. And so then the cost function is the typically the mean square error. And so it's just the sum from from 1 to the number of data that we have of P R, and I put the number of the configuration number as an exponent minus K equals 1 to capital K, P from 1 to NB, theta P, d RKR, I E squared. So that just means minimizing the mean square error between the total energies and the total energy approximations. And so here, maybe one important remark is that we can reorder the sums here. And so what we have is that we have the terms that appear here are really the total energies. And so we never train on the local energy contributions because we don't have access to this data. So here we have this, and then d RKR P squared.
P from 1 to NB.
Yes, and here this is wrong. Yeah, thank you. And so I think it's a really important point to have in mind that you never train on local energies. You always train on total energies because that's the data you have access to. But in afterwards, if you want, you can see how these local energies look like in your function because it's well defined. But in the training, you never see that.
This way, in that state.
Yes, exactly. But then I want it to be symmetric with respect to. So if yeah, exactly. I cannot put a P. Okay.
Yeah.
Yes. Yeah. Okay, and so this is a quadratic functional in theta, and so when you want to optimize this, when you minimize the cost, you have a linear system to solve, and this linear system is of dimension the number of descriptors that you have. Okay, and so this is used a lot in the literature. So I basically mentioned all the methods. I mean, not all, but a few methods in terms of descriptors. Now that's kind of the same method, but in terms of parametrization. So moment tensor potential, so MTP, by Chapev, is a method using a linear parametrization. One interesting aspect in this work is that basically he didn't have a way to generate a basis of invariant polynomials. So what he did is that he put everything in the basis functions here, and then he used lasso regularization to sparsify, and so to reduce the number of parameters at the end. So that's that one work using lasso regularization in this context. Then there is the permutation invariant polynomials potentials, sorry, I talked about yesterday by Brahms and Bowman. So that's also linear parametrization. So that's 2009. Then atomic cluster expansion. That's Drauts, 2019. The snap potential is also linear. And so somehow my feeling is that at some point people were doing a lot of kernel regression and then kind of moved to directly like linear methods. And with and try to optimize the descriptors themselves.
The spirits that they do arbitrary to generate some data and then they train.
Yes, yeah. Okay, so for the data, you would have typically DFT data. You generate a database varying the configurations depending on what you are interested in, and then you would fit this, and then if you want to run a molecular dynamic simulation, then you would use the potential that you had fitted, and you hope that it doesn't explode or things like that. So actually, when I worked on the permutation invariant potential, so the atomic versions, so what was really nice in that context is that we could actually, since we have two-body potential, three-body potential, etc., we can actually plot the two-body function and see what it looks like. And so we were using polynomials, and so the first version of the two-body potential, where we didn't put any regularization, was looking like something like this. Not even, so I think it was really something like strongly oscillating, so really nothing kind of physical. So we showed these to our physicist collaborator, and he was like, yeah, no, you cannot we cannot do that. And so what we just did is that we added a regularization using the Laplace, so second derivative of the energy. And so then we got something very, very nice, very smooth, and really looking like perfectly. And so this was really a nice surprise. The other thing that we did to kind of ensure that we could run MD with the potential was to kind of from some kind of limit radius to kind of enforce the behavior of the two-body potential, that it was really going fast to infinity. Otherwise, basically, when we run molecular dynamic simulations, the trajectory could just get stuck in holes, like really unphysical holes. So it wasn't really working. So somehow, I mean, in theory, it's just like choosing basis functions and doing a linear fit. In practice, you still have to tune a few things to make it really work. Okay, and so on the I would say main advantages of this method, so the cost of solving the problem is usually quite cheap because it's really just a linear system, so you can deal with a pretty large dimensional system. And then also the cost of evaluating the function afterward. So to evaluate the energy, you only have to evaluate the descriptors, basically. So it depends on the cost of the descriptors, but in principle, it can be very cheap. And also, since you have a nice looking expression for the energy. You have an explainability which is in general better than for other models. Okay, so I think I will stop here for the break, and we'll do Kernel methods afterwards.